I'll let you read it.
Okay. And is this button to go? Nice. Okay. Ready. So, hi everyone. My name is Parker Cole. A lot of you know me, some of you don't. Today I'm going to talk about my research, which is on graph neural networks with phase-space analysis. And if you don't know what that means, that's okay. That's why I'm presenting. And I just wanted to thank everyone for being here. It's somewhat early. I mean, it's School of Computing early. So, yeah, I'll get right into it. Here is a brief outline of the presentation.
You're gonna sit down, you're blocking your screen.
Brief outline of the presentation. So first, we're going to start with just an introduction to the problem. A lot of you might be aware of the term rootkit, and what that is basically just it's a type of software that someone can exploit that likes to hide in your computer and give them elevated access. There's a formal definition up here for you if you want to know, but that's basically what we're trying to do is detect rootkits. There is already a few ways to do that, but those aren't fun. There's drawbacks to every solution, and so more solutions gives you more tools. So the current solutions involve looking at the current system stack, the assembly that's being executed and, the actual state of the computer, which can be invasive, and it also has some technological overhead. So if you wanted to run something like, let's say, Norton has its own problems with interfering with software, but also, it's going to have overhead on the process. And if you're running a cluster or something, you don't really want that. We also have side channel analysis. That is another promising sector. There has been some work done on this already. Side channel is simply a metadata part of the computer, whether that be power readings, signals, any kind of side effect from the hardware or the computer as a physical component. There has the specific way that I was going to look at them is with power. This is the paper that first kickstarted my research into it. Neural network analysis of system call timing for rootkit detection. That's Patrick Luckett, Dr. McDonald, Joel Dawson. And there are different side channels, but power is the one that I'm going with because a rootkit likes to have elevated access, sometimes ring 0 or even ring -1 access. So if you can look at side channels, you can't bypass that. But if you have something like a hypervisor and the rootkit goes above that, then it can bypass that. So this is kind of a fail-safe way to look at it through the context of hardware. So once we have the power analysis and we know that there is a way to detect rootkits just by looking at the power draw, the sequences of voltages drawn by the computer, we still have work to do along the lines of how do we do that and how do we analyze it? Phase space is a very popular topic here itself, but I will go over what it is if you're not familiar with it. What is very important for my research is Becca's work. It is side channel detection for rootkits. She is using phase space for detecting rootkits based on the power data. There are, I don't want to say downsides, but every solution has upsides and downsides. That's an engineering principle. So the things that I want to tackle are a more generalized, even if less accurate result. We want something that can be used for in mass, without user interaction too much. So that introduces machine learning to it. What Pekka is doing does not require machine learning specifically. It is called thresholding. I'm not the expert on that topic, so I'm not going to say too much about it. But basically, it's form of pure math that looks at different parameters for the phase space algorithm and tries to. It's not clustering, but it's along those lines, if I'm understanding correctly. Machine learning would be a helpful introduction to this because machine learning algorithms tend to be faster, a little more generalizable. They might sacrifice accuracy in some contexts. It depends on the actual situation. And a great paper that I found, Chad, do I say you're in Calgary?
Yeah.
Okay. Well, your paper was great. It actually did explore face-based analysis with machine learning. So that was a great precedent for me to go, okay, there might actually be something there. Um, However, I will talk about later how I wanted to take a slightly different approach for a couple of reasons. There's the drawbacks of convolutional neural networks. I'm going to talk about isomorphism in a little bit, but the main thing is that phase-space analysis creates graphs from data. Now, a graph, the way that a convolutional network works is it takes pictures of these graphs and classifies them. According to graph theory, which I will go over later, no need to get tripped up on this, there are several ways to draw the same graph. This is a very famous one known as the Peterson graph. All of these graphs are equal, but their pictures are very different. So that's the problem that I'm attempting to solve. Also, convolutional neural networks have a fixed image input size, which means that if you're drawing your graph, you can only have so many edges before it starts looking like a black ball.
So most CNNs actually you're feeding a picture of the graph?
Yes. So the convolutional neural networks, from what I have seen, you can correct me if you're wrong, it is your work, but I was seeing that there was projections or embeddings of them as an image. Is that correct?
Say that one more time.
You were using images of the graph for encoding.
No. You come on, yeah? No.
You still won't define it. It's more of a time series model, and then we run all possible calculations, choose the best. So we're not technically learning.
Okay, well, I have seen another paper. It's in my references later. There has been work done with the actual images of graph. I apologize for misattributing
No,
it to you, but
That was Patrick.
that was Patrick Luckett. I am so sorry. There is a couple papers that I've been bouncing across. Oh, that's
But we do consider isomorphisms because we're looking at graph similarity.
it's just it's a challenge that has been addressed, but it is a challenge.
But I didn't realize that was actually what other people actually do. They take images of the graph, so. But then you have to choose a layout.
Yes, and
Yeah.
it's very hard to find a canonical form of a graph.
Okay, all right.
So this is a little bit of literature review, a little bit of background for all those terms that I've been using. Again, the main problem that I want to solve is both the isomorphism and just a way to encode stuff more efficiently, possibly. First thing, hot topic, nonlinear phase space. What this is a method of taking linear time series data and making it into a graph. How does it work? Just a very rough overview of how it works is we have, imagine this is our time series data right here. This is just, it can be readings from a sensor or something. This is our symbol table. We are going to decide buckets and assign them symbols. First step is to symbolize the data. Again, just an example. One of the hyperparameters that you have to choose is the size of the buckets or symbols, if you want to call them that. And then the second step is to turn these into actual vectors. I'm choosing every yellow one for a size 3 vector. Again, with every 3. These are more variabilities in the process that you have to form these. Once we have our nodes of variable size and from skipping every nth item in the list, we're going to do that similar method for edges. This is going to generate the graph. And there's a little bit of theory behind the graph that we're making. This graph is not necessarily connected. It can have multiple components that are separate. So that actually is a challenge for a lot of machine learning as well. A lot of graph convolutional networks, what they like to do is assume that every graph is one connected piece. I already talked about isomorphism a little bit, but there's infinite ways to draw one graph. These two graphs are the same, and even if you were to try to canonically draw them, a big issue is this looks the same in the matrix form.
I think all of our graphs are connected.
Sorry, from like right here, BAA, for example, could connect to something and they could be interconnected from what I've understood. Like-
So ACC and BAA and C, those are a composite node.
These could be totally independent. Am I wrong?
No, so each of your little ACC, BA, that is one node.
Yes.
So in the sense of, there are no unconnected nodes.
What I'm meaning to say is that the graph, everything is connected, but it's not fully connected so that you could separate the entire picture into
There
two
are a lot
graphs.
of components.
Yes, that's what I'm meaning to
Yeah,
say. Yes, fully connected in this context just means you cannot draw a path from one to another guaranteed every time. And that is a challenge. So here's my proposed solution that solves the isomorphism problem while still being a little bit more efficient with the data in terms of how we are learning. Graph neural networks, they are a class of neural networks that you don't really see a lot of, just because there's fewer graph class problems than other classes of problems. There is quite a few graph neural networks that exist that is not just a specific model. Is there one? Oh, sorry.
Talking to myself.
So theoretically, it would require less pre-processing time. Embedding a graph, a very complex graph, does require quite a bit of overhead. If you could work with the matrices themselves, this is just a visualization, but we are working with the physical matrices, not pictures of the graphs now. So that's a little more expressive, and they each do something a little unique with the graphs, but that is the requirement. It's not pictures, actual matrices and adjacency matrices.
How about one? I would just mention, I don't think you can say you've solved the isomorphism problem, just so you know. It's like telling computer scientists yet you've proved something, right?
Yes,
So that
I
is an incomplete problem, and
Yes.
so I think what you mean is you've made it very efficient, right?
yes,
Yeah.
that's I'm
There is
tackling, I'm
computation, yeah.
attempting to solve.
You
There's
gotta realize, so really, you are essentially asking the same kind of questions in terms of similarity with this graph neural network. That's really, so you're doing something very similar that our current way of doing it is already,
a
okay?
yes.
Okay.
It's just the way that it handles it. It's summarizing it's condensing the graph and throwing away useless nodes, and it has a way of
Okay.
ranking those for efficient pooling. So the purpose of the study and where I come in is I'm trying to find out which graph neural networks work the best. There is no definitive answer, but I have to look at specific examples and try to compare them. Is there evidence that this is a better method than traditional methods? Or, there's not going to be objectively better. There's going to be some upsides and some downsides. So if it does beat out the competition in some ways, what are those ways? Is it faster? Is it less overhead? What are the trade-offs? For the experiments that I'm actually planning on running and have ran so far, I want to apply graph neural networks to data sets that have published results on them already. That has been completed. I just got some wonderful new data for me to validate the models that I've trained. So that is in progress. After I validate my results and know that I have some working graph neural network models, I want to compare them to existing research papers and try to see how this stacks up against the other methods. And then I would like to, that's your data, the traffic data. I want to also apply these not just to rootkit detection data, but I'd also like to apply it to network trafficking data, just to kind of see what works and what doesn't work with graph neural networks, and if they can have a higher or lower accuracy. Future work. This is stuff that I either plan on doing or would be a lovely topic for another person's thesis. When you do phase space, the algorithm, you have to find the proper parameters. And is there a more efficient way to find these? Can you perform something like gradient descent and try different hyperparameters to allow you to get more efficient answers? What ensemble methods could help? Later on, I will show you that graph neural networks tend to work better with more specialized data. So if you could maybe decision tree multiple versus just one graph neural network, does it work better? This was an interesting question that was raised, is can we do like multi-dimensional graphs from different sources and stitch them together? That's a very interesting question. And the rest I'm about to go over. So these are some preliminary results and what I've done so far. As we can see here, there's many different types of graph neural networks. I've tried a lot. I've discarded most of them that just say 50% across the board. But I've narrowed it down to the GIN, which is the Graph Isomorphism Network. It's dedicated to isomorphic problems. GraphSage and EdgeCNN, which just focuses on the edges. From my results so far, it seems like GraphSage and EdgeCNN perform the best. We do have a bit of weirdness when it comes to the results from EdgeCNN. It's very shaky. I'm curious to see how it'll perform against the new validation data. But so far, these two, GraphSage and EdgeCNN, are my best candidates.
Tell me again what an epoch is.
So an epoch is one run through your training data. So you're going to train one time and then test with your testing data. So then keep doing that.
Is it kind of like cross-fold validation?
Yes, except that you don't want to mix the things that exist in A will never cross over into B and vice versa.
Okay.
Cross-validation is used for a earlier model, but this is the most efficient way that I've read for
Is there a limit on the number of epochs based on how many divisions you can have? But that one says 1,000. So
Yeah, no, you're allowed to do because what I'm doing is pouring over 70% of the data and then 30% is holdup. So I'm doing one training,
Okay.
validation, one training, and then gradient
It
descent.
doesn't infinite.
You could go over the training data as much as you want, but the accuracy will start to bottleneck, but you can run as many epochs as you want. And then that's what the validation sets are for, is to make sure after I'm done all my training that I didn't overfit, that I'm actually solving the problem. Preliminary results also show that with the rootkit data, we had Linux and Windows files, and I found that the Windows performed very high accuracy very quickly. The more generalized problem, it's kind of shaky when you mix Windows with Linux. However, over time, this is a lot of epochs. I have reached 99.6% accuracy with the mixed data. Again, we want to validate that, so I can't publicly say 99.6 guaranteed. But from the training data, it seems to have gotten there. This is also just a comparison of how each different type of file behaves. And then we talk about the actual validation. I want to eventually validate my results, and then I can compare them to the published results and to see if graph neural networks are useful and a novel way to approach space-based graphs. Are there any questions?
I got a quick question.
Yeah.
Actually, a couple. What do you think are the advantages of using machine learning, more specifically deep learning, over the more traditional signal processing approaches to analyzing your data?
Well, since this is time series data that we are harvesting from a computer, we can actually theoretically get quite a bit of data from just one computer. Scalability is an important aspect when you're looking at this kind of stuff, because with a model, we can get 1 million readings over the course of 5 seconds if you want to, and feed them to the model, and it needs to run locally, so less overhead is important. So scalability and overhead, yeah.
So you're saying that since we usually signal processing doesn't necessarily require a whole bunch of data, but since we have you have the advantage of creating tons and tons and tons of data, why not take advantage of the newer, more better approaches than using signal processing? So in other words,
Yeah,
take advantage of,
exporting the abundance of data.
okay. And just a second question, what are some of the, you use 3 different models, one model is not so good, but 2 are good, but how, just to have a feeling of how many hyperparameters have you used? So for example, dropout rates, have you used like 3 or 4, learning rates, maybe 1 or 2? Have you done any kind of cross-validation to kind of reach an optimum there, or?
So I have tried a few methods, such as dropout layers. Cross-validation is a thing that you kind of have to train completely differently for. I've tried also to run something called a hypertuner. This automatically performs gradient descent on the parameters that you have, and it has suggested optimal learning rates. I've tried a lot of them. I have tried batch normalization. That's an important thing that I've also included into it, as well as a lot of other things like KNN pooling that didn't work. So I think I've gone through probably about 30 different ideas for the internals of the model before arriving at something that works.
Right. So it's not just an artifact of your choice of hyperparameters that you arrived at, say, SageGraph being your best one.
Oh,
It's
yes.
just
I've tried about 12 different graph neural networks.
Okay. Thank you.
Thank you. Anyone else?
So there's 2 papers that Patrick did. One actually used hypergraphs.
Mhm.
I don't know if you've read through that one. We should talk about that one.
That might have been the one that I was confused with.
Yeah, we should talk about that one sometime. And then there's another one where we were looking at graph properties of the phase-based graphs.
Yes.
And it is kind of mixed results on that one, but we were looking at we didn't look at the mu subgraphs, but the cut set graphs themselves. I wonder if the mu subgraphs might be better, but that was looking at, I think it was 12 different properties that were, for the entire graph. And I think connectivity was a lot. There's several related by connectivity and things like that, number of connected components. But it didn't really improve the traditional way we were. But I think what I told him to do is see if that might help improve the normal thresholding success occurrence things. So it might be something you would think about too, is using that type of information to tweak or tune. I don't know.
That's when I input the data into the graph neural network, I've had a few ways of encoding it.
Mhm.
One of them is because you have unique and you have the unique versions of the graph and then the non-unique, which is much bigger. I've found that the unique ones, but weighting each node and each edge based on how many times they occur does yield better results. So a couple more graph features could be helpful.
Okay. So you're actually using weighted edges.
Yes.
Okay. Good.
And directed versus undirected, we've had a little bit of discussion, but I would like to try them both just to see. Never know.
Okay. So all the graphs that we've given you are going to be undirected.
Yes.
Yeah.
Anything else? Yeah.
So what I've given you so far is all like side.
Yeah.
Or when are you going to like start looking at other parameter sets, or are you?
Well, I would like to have definite train. Like we know that the ones that you gave have some kind of logic behind them and that they yield something. So I'd like to have that as like a held steady variable at first before we look at other ones. But really, I use whatever data I can get.
But yeah, because McDonald gave you ones that had bad results.
Really?
So I'm curious to see what happens and how you're like gonna see if it outperforms versus if we give like a better set.
But yeah, I've only looked at the sets that I've been given. I wasn't even aware that those didn't work out well for the other method.
I've told you that now 3 or 4 times.
I get told a lot of stuff. I forget sometimes.
But
You sound a lot like
McDonald
McDonald.
has asked them to hold off before we actually get a procedure in place.
Yeah, I'm just curious how like which ones you're wanting to look at because there are so many different.
That's gonna be.
Address that. Yeah.
That's fine.
that's also part of the future work is now that we have a neural network that you can actually run 5 epochs, which is very fast, look at, try a different one, 5 epochs. You can actually perform gradient descent on the hyperparameters, which is what I've done to arrive at certain settings for my current model. Is that all the questions?
I have 5 or 10,000 more.
Yeah.
I'm interested.
Well, that's all I got. Thank you everyone for listening to me talk about my research, and if anything interests you about it, I'm happy to answer any other questions you might have. If you need a thesis topic, future work.
I think Burke's up next week. Good deal. All right.
Stop this recording.
Yeah, you saw it.